We're going to go in a new direction now of FM synthesis or frequency modulation. This discussion is going to parallel our discussion of amplitude modulation, where, if you remember, first of all, we talked about multiplying a signal by an envelope, which is kind of a slowly moving shaping function. Then we talked about multiplying by a more rapidly fluctuating signal to form amplitude vibrato. And then finally, we talked about multiplication by audio rate signals, doing amplitude modulation, where there we started with sinusoid, and when we multiplied by a modulating sinusoid at audio rates, we found that the result was taking this original signal and pushing it up by the modulation frequency, pushing it down by the modulation frequency, forming the sum and difference frequencies. And so something along those lines happens with frequency modulation at audio rates, and it leads to a very powerful synthesis method called FM synthesis. So that's where we're going. Frequency modulation occurs naturally. Voice inflection, voices have natural jitter. Singers use vibrato. Vibrato is applied in instruments. Here's an example. Okay, that's someone with a guitar probably pushing the string up and down or varying the pressure on the fret to change the frequency. And there are more extreme effects like electric guitars with whammy bars. Another place you see frequency variation is that many musical tones begin low and come up to pitch, especially untrained singers like me. And that's a kind of frequency modulation or frequency change. Another cause of frequency change is that vibrating strings, when they are bowed or somehow driven to higher amplitudes, they stretch more, and the stretching causes them to go sharper as they go louder. Other instruments are designed for extreme frequency variation. The slide trombone, the theremin, the voice, the violin can all create melodies by essentially playing a single tone where the frequency is being changed. Here's an example of a theremin. So there are three main ways to create frequency modulation with Nyquist. One is Nyquist has a built-in unit generator called FM Osc, so Osc is short for oscillator, and the parameters for that are a basic pitch, or kind of central pitch, as if there was no modulation. And then the second parameter is the frequency modulation, which is the deviation of frequency measured in hertz from the basic pitch. And then there are some optional parameters to specify a table and a phase, just like in the normal Osc unit generator. The second method is Hertz Osc, which is similar to FM Osc, but rather than giving a basic pitch in steps and a frequency control in offset, you just give one parameter, which is the absolute frequency that you want. And this parameter can either be a number, so you get a fixed frequency in hertz, or it can be an envelope or a more complex function that gives the changing frequency over time. And the third method is a little bit obscure, but it sometimes can be very useful, especially for applying frequency modulation effects to sampled audio that you might read from a sound file. And this is the function called SND-compose. Okay, so the compose here is referring to mathematical functional composition. Sound compose treats the two signals, F and G, the two parameters, as functions of time, and it's actually forming the functional composition. So in other words, if the parameters are F and G, we're computing f of g of t, where t is time. And depending on what g is, you can achieve some very interesting effects, essentially speeding up and slowing down the time parameter that's passed into the function f. So we're going to use all of these in some exercises and then continue with more discussion of frequency modulation.